Hey, hello everyone. So welcome to this talk. So I'm Shuai Wang. I'm from Hong Kong UST, and this work is a joint work with my colleague Chengyu Zhang and Zhendong. So most of this work is done when I was working at ETH Zurich. So I need to mention that. All right. So blockchain is a very successful application of crypto system. So generally speaking, like the blockchain is a list of records, and in each block we have the timestamp, we have the list of transactions, we have the hash value of the previous block. So it's kind of like a long list. So generally speaking, the blockchain was designed as the core component of the cryptocurrency Bitcoin. So that's kind of like the core player in the Bitcoin system. And generally speaking, for the Bitcoin, we have lots of users. Each user is played as a simple bank account, and they can essentially schedule transactions to send and receive money through the Bitcoin system, and will be kept tracked by the blockchain. So and besides the Bitcoin, there's another super popular crypto system called Ethereum. So that's our key focus today. So generally speaking, the difference between the Ethereum and the Bitcoin is that essentially you can think about the traditional mobile phone and the smartphone. So generally speaking, we use the Bitcoin essentially similar how we use the traditional mobile phone. We simply use schedule some transactions to send and receive money. It's essentially comparable to how we use the traditional cell phone to make phone call and receive phone call. That's it. But on the other hand, the Ethereum is a much more flexible system in the sense that we not only use our mobile phone to receive and make phone call, we also install some applications on our mobile phone. So that's comparable to how the smart contract works on the Ethereum system. So generally speaking, the smart contract is kind of like a software, encode whatever computation functionality we want, and we essentially deploy the smart contract on the Ethereum. So that will definitely make the Ethereum much more flexible. In that sense, we not just send a transaction, send money. We can encode whatever we want, whatever logic we want. But on the other hand, because of the smart contract, because of its flexibility, it can actually enable lots of very subtle attack, something we're not fully aware of, but it could cause a lot of issue. So that's actually our topic today, smart contract. So this one gives you all a very high-level idea about what is smart contract. So generally speaking, the Ethereum system. So there are kind of the user, the account of the Ethereum system could consist of either the user, maintain some private key, or it could consist of the online contract, some existing smart contract on the Ethereum system. So essentially, they can issue some transactions, and the transaction will be uploaded to the pending transaction pool, and it will wait until the miner got pick certain transactions from the pending pool and execute, and then append to the block. So one issue is that generally speaking, the pending pool has a very large size comparing to the size of each block. Roughly speaking, the pending pool could consist of over 10,000 of pending transactions. But each block will consider roughly 500 or 600 transactions. In that sense, each transaction will wait for a considerable amount of time before it is executed. And more critical is that essentially the miner is free to pick whatever transaction and in whatever order he wants from the pending pool and execute and append it to the block. In that sense, for example, a user submit a transaction to the Ethereum system, he just cannot guarantee his transaction will be executed before some other transaction after his transaction. So that's the tricky thing here. And generally speaking, in that sense, we consider that's actually one source of non-determinism, right, in the Ethereum system. In a sense, the order of transactions is essentially unpredictable to the users. And this one gives you some idea about smart contracts. So generally speaking, in the smart contract, we have lots of functions. Each function will be executed within one transaction. And we have some so-called global variables. So essentially, the global variable, they are kind of persistent across different transactions. In that sense, different transactions will manipulate the same global variable. I can also have some local variable. I don't have local variable in this case, but generally speaking, local variable it's just temporary within each transaction. And very important, it has a very special statement called a payment statement. So essentially, for this case, the owner is the address of the money receiver, right? we send money to the owner, right? This is address. And the amount, like message.value minus like fee, that's kind of the amount of money we are going to transfer to the owner. So that's a very special statement called like the payment statement. So payment statement can initialize some like money transaction, but it can actually lead to some like very subtle issues, as I will mention here. So for example, like we have like transaction schedule a payment statement, and we'll call the like the owner transaction. So what could happen, like in general, is that in the middle, right? There's a so-called cross-contract call. Essentially, we start from the caller, and then we go to the callee. That's the normal case. But what you are probably not expecting is the behavior of the callee function. So callee contract. So generally speaking, although there are some constraints, but generally speaking, like the callee can do whatever he wants. For example, he can like go back and trigger some like function of the caller, or like it can even call some other contract. That's something you cannot assume. And generally speaking, that's also one source of non-determinism in this research context, in the sense like the callee behavior is unpredictable, right? It can like re-enter the caller function, something like that. And right, there are other some like subtle issue. For example, like when we do a gambling like a contract, we can either like fetch some system dependency like timestamp, something like that, and then compute a random number. So you are expecting this one is kind of like random, but it's not true. It's not true. Actually, this one, some system information property can also be manipulated by some malicious miner or some other adversary contract in some sense. So in that sense, like this one, the system properties, some transaction properties, is also non-determinism in the sense like you just cannot trust it as fully random, as real random information. So yeah, there are lots of cases here. So that's a rough idea. So generally speaking, the message we want to deliver is that, like, if you look at the big picture of the Ethereum system, so there are kind of lots of like source of non-determinism. So for example, like the system property, some transaction property dependency, and also like the unexpected behavior of the external callee, something like that. And as I mentioned before, like you just cannot assume the order of the transaction will be executed as what you are expecting. Those something like you just cannot assume. And our observation shows that actually those are actually the root cause of much confusion to the users. And actually it leads to lots of like the common attacks, common payment bugs, like that is disclosed in the real world. That's kind of like the root cause of such common vulnerabilities, common issues, as I will mention in a minute. So let's look at like a very popular attack that's called a reentrancy attack. So generally speaking, we have an attack contract, we have a bank contract. So essentially, like in the attack contract, is this function attack will initialize a transaction to the withdraw function. So this one, like the ideal case, is this one will like check the balance of this attack contract, and then like send the money, its balance back. So this one will go to the function with no name. That's called fallback function. Right? The money will go to this function. An ideal case is that after the execution of this function, it will return to the call set and continue execution, so on and so forth, right? So that's kind of like the expectation of the bank account, right? That's the expectation. But the tricky thing is that if you take a close look in the fallback function, you will realize there's another iteration of withdraw function call, right here. So what does that mean? So generally speaking, what would really happen is like when we execute to this part, we'll again like call this withdraw function, and like check the balance, and then like again send the money back to the fallback function, and again and again. So form a loop, right? Form a loop to keep like withdraw money. So the problem is that because the last statement will reset the balance of the attack contract. This one is not executed yet. And in that sense, according to the record of the bank, so this one, like the attack contract will still have like certain amount of balance. So in that sense, we'll keep execution until like the whole balance of this contract, this bank contract will be like run out. So that's actually the problem, and that's what would really happen in the reentrancy attack. You see, like it's keep going this way, right? So again, the problem is that, like I mentioned before, like we just cannot assume like anything. I just cannot assume the behavior of the callee. So that's the non-determinism here. So what would other people do, right? So generally speaking, this one is disclosed for a while, for several years, and cost like millions like loss or financial loss. So other people like has been coming out with some like a pattern-based detection method. Essentially, they try to like come up with a pattern. For example, for this case, we have the pattern like no write after call. That makes sense, right? If we can check that there's no write, there's no like update of the like persistent storage after the call. In that sense, we are kind of like detect some certain issue that can potentially lead to the reentrancy attack. That makes sense, right? And also people has been like similar thing, right? Similar pattern to detect this highly suspicious, highly vulnerable pattern. But the problem is that such vulnerability checklist-based method, right? They could be trapped by some subtle issue. For example, like this year, the smart contract has an upgrade. And after upgrade, some previously infeasible attack become feasible, which violate this pattern, but still like perform some reentrancy attack. And also like, well, right, very intuitively, like if you keep maintaining a vulnerability checklist, you have to keep extending this list with some expertise effort. And likely, you just cannot detect a bug until it become like notorious, like infamous, right? So you just cannot detect some zero-day problem, right? That makes sense, right? So that's the problem of existing research. And that's something we want to like address from the more principled way. So generally speaking, like we consider our observation shows that nondeterminism as the root cause of many common vulnerabilities of smart contract. And intuitively, so we try to like analyze the nondeterminism, right? Analyze how it would influence the payment, contract payment, right? In that sense, we kind of like conceptually capture the upper bound of all the like the conceptually capture the upper bound of this attack surface of a smart contract. That's our motivation. That's our like observation. And we actually divide like the existing vulnerability of smart contract into like two categories. The first one is called the NP1 bug, non-deterministic payment 1 bug. So this one will include some like popular attacks. And second one, the NP2 as well, include some like the reentrancy and the TOD attack, right? So generally speaking, like we try to model the root cause, like the chain of like the attack. Essentially, for example, for the NP1 bug, it's originated from non-determinism, and then for some local variable is influenced, and then like it affects the payment, something like that. The same thing goes to NP2, right? Affect the global variable and affect the payment, right? So in terms of methodology, right, to detect the NP1 bug, we need to analyze non-determinism and their influence on local variable. So this one is it's easy, right? So generally speaking, we can just pinpoint some usage of the non-determinism features, right? And then we can like analyze which local variable is initialized or assigned, right? So in this case, we can just capture some like non-determinism features from the smart contract. But the problem is that like to analyze the global variables, like which is influenced by the non-determinism, that's not an easy case. So generally speaking, like conceptually, right, there are some like non-determinism factor could affect the global variable. For example, the transaction scheduling, like I mentioned before, and also the unpredictable behavior of the external colleague. So what we are doing is conceptually similar to how people handle detect the global variable under the risk condition, right? So conceptually similar, right? So essentially, because like global variables, they are kind of like influenced non-deterministically, it's conceptually similar to how global variable is accessed within a risk condition, something like that. I will explain later. Right, so this one, like after we figure out this interesting like variables, we just do essentially like an information flow analysis and detect their influence on the payment. Right, so our assumption is that such influence is typically unwanted and enable some common attack. But I have to mention that one is consistent with some like observation from the common attacks. But I have mentioned that there could be some false positive since some influence is wanted by the programmers. So this kind of like the workflow I will just quickly go through because I have mentioned that. So we start by reverse engineering some like the online smart contract, the real smart contract running on the Ethereum mainnet. So that's kind of like the bytecode format. So we do some lots of reverse engineering effort. So this one is actually not very easy. You cannot expect like you make a cake or eat it. It's not that easy. So there's some like tricky engineering effort. And then we start to do the information flow analysis to detect the NP1 bug. And then like essentially to handle the more subtle global variable influenced by the non-deterministic feature, we can like start from the instrumentation. Essentially we'll follow like how the multi-threading program is instrumented, like to make it more analysis friendly, something like that. So it's a pretty standard technique. So and then like we do a model checking, and then essentially it goes to the pendant analysis. Again, we analyze how the some interesting global variable, how it will influence the payment. All right, so that goes to the evaluation part. So generally speaking, we have we collect over 30,000 online contracts from the Ethereum mainnet. So that one is most of them does not have the source code, only the bytecode. So we can analyze the unique contract by computing the MD5. So we have over 3,000. And then we compare with some state-of-the-art work and to demonstrate our the idea here. So the first one is about some case study here. So generally speaking, we try to analyze our technique and also some existing technique with some recently disclosed vulnerabilities and also some so-called variants of some common issues. So we try to analyze whether in such a little bit more challenging setting, whether the existing bug detector can still find the issue and what is our performance. So good things the evaluation is mostly promising in the sense by successfully capturing the root cause of such kind of the vulnerabilities, right? So we are actually more comprehensive than the existing research, right? We can successfully capture all the vulnerabilities, but they can miss some issue. The second thing is about the general evaluation here. So generally speaking, we evaluate all the cases and we interpret that we have comparable performance compared to the some other existing bug detector. So that actually makes sense because if you take a close look in our paper, you will realize that we have slightly drifted threat model. In that sense, we are not exactly focused on the same thing. So that could cause some drifting about the comparison here. But generally speaking, we have comparable performance. And to mention we have some analysis timeout. That makes sense because we use the model checking, bounded model checking. We have also some analysis failure. So generally speaking, we confirmed with the reverse engineering developer, and that's mostly because of their tool, the issue in their tool, right? So something one step further, so we try to analyze the agreement of our finding with some other existing tools. So we interpret the finding as generally promising in the sense we have more agreement comparing to some other bug detectors. So we can have more agreement overlap with their tool, right? So one interesting thing is we'll take a look at this paper on the account. You will realize in the smart contract bug detection, because of lots of issue or whatever, threat model drifting, people do not usually have much consistent findings here, right? We also have some manual investigation about because we have lots of bug with the bytecode format and only a few has source code. So once we have the source code, we can directly go into the details and verify whether our analysis is correct or not. So we have such findings. And we have some false positive, either due to some imprecise reverse engineering analysis, and also due to a little bit of strong assumption in this work. In that sense, we assume, like I mentioned, we assume any non-deterministic variable influence payment, which is unwanted, but actually there are some cases that is wanted, that is intended behavior of the contract. All right, so that's it. Thanks.